Okay, good morning all. If I am audible, please comment in the comment section. Okay. So in the last class, we were looking into a few properties of DTFT. So here we have seen all the properties and their proofs. Okay, time shifting, frequency shifting, differentiation in frequency, convolution, modulation, and coming to the Parseval's theorem. This we need to discuss today. Okay. So Parseval's theorem says actually, okay, the energy in time domain. That is one uh, aspect of Parseval's theorem. It's one like we can say deliverable of Parseval theorem is okay. Energy is same in okay both time and frequencies. Okay. So it's like in time domain, we have it's like time means we have the discrete time and continuous time. In this, we deal about the discrete time signals. For discrete time signals, energy is given as okay discrete time. So this is summation over n. Okay, x of n. Actually, it is mod x square of n, or you can write it as x of n into x star of n. So if x is real, then it is x square. If x is conjugate, then it is mod x whole square. Okay, so that doesn't the actual definition for a complex signal. This is the derivation for the complex signal. Okay, so what Parseval's theorem says is okay. For example, you have uh, in the place of we just will take this consider this case. Okay, and okay, let me use another app whether it is clean or not. Yeah. So consider this case summation x of n into y star of n. Okay, n is varying from minus infinity to infinity. So what we can do is we can apply we can substitute the DTFTs of both. Okay, so summation over n. For this, the DTFT is 1 by 2 pi integral inverse DTFT we substitute x of omega e power minus j omega. e power plus j omega n. This is over minus pi to pi. And this is one term. Just in order to what we say differentiate, okay, so we'll just put 1 by 2 pi integral minus pi to pi the conjugate of this one is, okay, y star of omega, y star of I'm writing theta in the place of omega just for differentiating these two are separate integrals. So e power minus j, because conjugate is there, you will get minus j, okay, minus j theta n d theta. This is another term. This is y star of n thing, okay. So now what we do is we take this summations, okay, inside, because integral is a linear operator, or 1 by 2 pi whole square you can put to one side, and you have double integral. So x of omega y star of theta summation, when you combine these two, this is e power j omega minus theta of n, okay. Okay, this is double integral. One is with respect to omega, one is with respect to theta, both varying from minus pi to pi only, okay, d omega d theta. So what is this value? So in this equation, this value boils down to, okay, so whenever this is like minus infinity to infinity, so this is like, okay, uh, so you need like whenever omega is equal to theta, or some integral multiples of omega is some multiples of, okay, omega is equal to theta, this value is e power 1, so it will go to 0, okay. So so let us okay, use this, uh, keep it aside, we'll come back to it. We'll use another page here, okay. So what does the modulation property says? So when you multiply two signals, okay, in frequency domain, they get convolved. Okay, this we have seen yesterday. So this is the convolution in frequency. Like this is, it should write. will give rise to the DFT of this one will give rise to x of theta y of omega minus theta d theta. Okay, so this is from minus pi to pi. So this is the DFT pair. If you have y in the place of y star of n. Okay, so what should be in on this side? So we know, okay, y of n, if for example y of n is having a DTFT of y of omega, so y star of n will have the DTFT y of minus y star of minus omega. So how it is okay, that means for example y of omega is this, okay, summation over n y of n e power minus j omega n is the DTFT. When you take a conjugate on both sides, this will become y star and this will become plus j omega. What you can write this plus as minus of minus omega you can write here. In this omega you can write minus, so that this will become when you y star of minus omega is what? So that is nothing but y star of n e power minus j omega n. So this is nothing but DTFT of y star of n is y star of minus omega. So here you will get so do one thing, you can just take this star to x. Anyway multiplication is commutative, so this will be x of minus theta you need to keep here. Okay, x star of, and this is y of omega minus theta d theta. So this is the modulation property. When one signal is complex or one signal is taken conjugate, what happens in the convolution? The corresponding signal x star of minus theta we will take. Okay. So then we'll proceed further. What we need to show is this one, a star of so y star of n. Sorry. So this is 1 by 2 pi integral x of theta y star of omega minus theta, omega, okay, this will be minus omega plus theta d theta, because we have taken y star here, so this will become here a Fourier transform becomes y star, and theta should become minus theta, so this will be plus theta. So here when you take uh, Fourier transform of summation over n, okay, that is nothing but so when you apply summation over n here, because of the linearity property, here also you will get summation over n. Okay, here we didn't wrote. Okay, okay, let us write as another step. So what is the meaning of this one is summation over n x of n y star of n e power minus j omega n. What is this one? dtft of x of n into y star of n. What is this? This one. Yes or no? So if you want only this term, let us say this is some p of omega, some dummy name. So p of omega is what? This everything is p of omega, which is the dtft of this. So if you want only this summation part, how should we eliminate this? If you take p of 0, will it happen or not? So what is p of 0 when omega is equal to 0? This is simply summation over n x of n y star of n. Okay, so that is p of 0. And what is p of omega actually in the frequency domain? This is what the p of omega is. So when you substitute omega is equal to 0, what you will get here? This is equal to, this is same as 1 by 2 pi integral x of theta and y star of omega is equal to 0 now, y star of theta d theta. D theta is cutting. Okay, so this is what we get. So now, is it clear to all of you? So we used this property of modulation property that we have proved yesterday, x of n into y of n, or here g of n into h of n if you take, that is the convolution between these two. So if you take the second signal as a conjugate, okay, so h star of n dtft is h star of minus omega. So in the play here the omega variable is theta in this integral. Okay, so this will become plus theta and you will get star here. Okay, so that's what it is. Okay, this is plus theta and it will be, you will get star here. And so what dtft of this is this. So what is dtft of this? In the expression, if you substitute, this is, let's say, let us we call it as p of omega, this one. So p of omega is equal to this. Okay, when you evaluate this, you will get this. Okay, so but we want only this summation n equal to minus infinity to infinity x of n y star of n. So this thing we want. So when you substitute omega is equal to 0, we will get this dc component. Okay, so when omega is equal to 0, you'll get this. And in the dtft frequency domain also, if you p of omega is this, when omega is equal to 0, you'll get this one. Okay, so now what we got finally is summation x of n into y star of n. If you take dtft of this one, not dtft, sorry, Uh, so this we got exactly equal to 1 by 2 pi integral over minus pi to pi. I'm not writing, so here it is over n. So x of theta into y star of theta d theta we got. This is exactly equal to this. So now when y of n is equal to x of n, let us say y of n is equal to x of n, what happens? This one on the left hand side, this is x of n into x star of n, which is same as mod x of n square, okay, which is equal to 1 by 2 pi integral minus pi to pi. So this is minus pi to pi. So what is this one? X of theta into y star of theta. This is x in the way, in the place of y also now we have theta. So x star of theta into x of theta is mod x square of theta d theta. So or since theta is the variable of integration, okay, you can just put it as omega also. That is, that is a just an integration variable. So what is this called? On the left hand side, this is Ex, energy in time domain. Okay, this is Ex, and from the Parseval's theorem, this has to be the energy in the frequency domain. So this is also energy, but how to calculate energy in frequency domain? Since the energy in time domain is equal is given as with this expression. So this expression, if you know x of omega, take magnitude square of x of omega and integrate from minus pi to pi and divide by 2 pi. This will give the energy of the signal. So this is called energy in finding energy in frequency domain. If someone asks you what is the energy of the signal by giving the spectrum, need not calculate IDFT. You just uh, substitute x of omega here and you will get this energy. Okay, is it clear? So we started with this. Okay, this is just a initial approach. Okay, again, since it is not easy to calculate this complex exponential infinite sum, what we did is we just used a trick. Okay, we used the modulation property. What does the modulation property says is when you multiply two signals in time domain, they will get convolved in the frequency domain. Okay, since the frequency domain is continuous, we have this continuous convolution. Okay, here also everywhere the integration, since it is discrete time, everywhere integration will be minus pi to pi. So when you take one signal as complex quantity, okay, one signal is complex, okay, so then the in the frequency domain, so in the time domain, if you take complex in the frequency domain, it will get flipped with respect to the uh, vertical axis, that is x of theta will become x of minus theta and it will get conjugate here also. Okay, so uh, now if you take conjugate for the other signal, so here also you the other signal will get conjugate and minus theta will become plus theta will become minus theta and minus theta will become plus theta, simple. So this is your modulation property for complex signals. Okay, if one of the signal is complex. Okay, let us means like let us call this frequency domain everything as p of omega. So what is this p of omega is actually the DTFT of this product of signals. Okay, So when you substitute this in the DTFT equation, that is P of omega. Okay, and we want let us find what is P of 0 when omega is equal to 0. Okay, if you substitute omega is equal to 0 here, so here e power 0 is 1, so you left with only this summation term, and in the frequency domain correspond, this is equal to this P of omega only. Okay, so this is equal to 1 by 2 by x of theta when omega is equal to 0, that is y star of theta d theta. Okay, all this we get this expression. Okay, from this when y of n is equal to x of n, what happens? This will become summation over n mod x whole square. Here also integration mod x of omega or x of theta whole square. Okay. So this is called energy in time is equal to energy in frequency. That is the Parcell's theorem. Okay. So moving on to the properties, few examples of some important properties. Okay. So there will be always our signals are not so simple. We have seen some what we call the DTFT pairs. Okay, some DTFT pairs we have seen in the last class, delta of n1 u of n, okay, alpha power n u of n, something like this. So and these signals won't be that simple. So if you take some complex signals like this, okay, some combination of this n plus 1 alpha power n u of n. Okay, how to find the DFT of this y of n is equal to n plus 1 into alpha power n u of n. So for alpha power n u of n we know DTFT. Okay, which is what is for alpha power n u of n DTFT, 1 by 1 plus a into e power minus j omega is the DTFT that we have calculated for alpha less than 1. Okay, this is alpha or a. Okay, 1 by 1 plus alpha into e power minus j omega is the DTFT for this. When you multiply with n plus 1, what happens? Okay, so you can just put it if you take this x of n, which you know DFT, so you know DTFT of this, you take it as x of n. So y of n is n into x of n plus x of n, because here n plus 1 is there, n into alpha power n u of n plus 1 into alpha power n u of n, alpha power u of n, if you take x of n, so you'll get like this. So have you seen this property somewhere? So this one, differentiation in frequency property. Okay, so differentiation in frequency property, what it says, if you know g of n DTFT, you can find the n into g of n DTFT as a differentiation of this j into d g of omega by d omega. Okay, so and x of n DTFT we already know, which is 1 by 1 plus e power minus j omega. So x of omega, this is 1 by 1 minus alpha into e power minus j omega. So this is what we got. This is the DT. Okay, this is minus. Okay, so this is the DTFT of x, which is x of omega. So if you want n into x of n, what you need to do is you differentiate this x of omega and multiply with j. Okay, so differentiate with respect to omega. So you will get this 1 by a d by dx of 1 by x is 1 by x square. Okay, minus 1 by x square, and the differentiation of alpha into e power minus j omega is alpha into e power minus j omega into minus j. So minus j into minus j will be plus 1. So this is the first term FFT DTFT, and this is the second term DTFT. From the linearity property, you can add these two DTFTs, so that overall DTFT is addition of these two. This will become like this. Okay, 1 by 1 minus. So this is the DTFT of n plus 1 into alpha power n u of n for alpha less than 1. So what we did is we used the properties. Okay, if you directly substitute this and if you try to do the DTFT, it is difficult. So what we used is we used two properties. What are those two properties? Differentiation in time property and the linearity property of DTFT. Okay, so you need to mention. So for exams like IES and all, you need to if your descriptive questions are given, you need to write every concept or every detail of the concepts what we are using. Okay, if you simply say that okay, the n into x of n DTFT is this, okay, it won't be considered. You need to say how it is this. Okay, because of differentiation property of DTFT, you can differentiate okay, like that. And you have to mention because of linearity property of DTFT, you can add these two, like that. So now the second signal, determine the DTFT of V of omega. So V of n is given like this. So this looks like our constant coefficient difference equation in one sense. In the place of y you have v, and in the place of x you have delta. Okay, so that means you are giving input as delta. That means v can be your impulse response. You need to sometimes correlate whenever you see a equation. You need to sometimes correlate with your past knowledge. Then you will get the intuition of the problem also. Okay, sometimes that concept understanding of the problem helps you a lot. Okay, so even though if you don't know solution mathematically, at least conceptually you will know the solution. This could be this thing, and you will try to do it in another way, another known way possible to you. Okay, so yeah, this is given, and you need to find v of del j omega, and we know the what is the DTFT of delta of n, 1. Okay, and what is the DTFT of delta of n minus 1? How you find the DTFT of delta of n minus 1? What property you use? We use time shifting property. So time shifting property, when you delay a signal in the frequency domain, a phase factor will get multiplied with the spectrum. Okay, that is e power minus j omega n naught, or e power minus j omega k, whatever the delay is, n naught or k. So here in the place of n naught you have 1. So e power minus j omega 1 will be multiplied to what is the DTFT of delta of n, 1. So yeah, so delta of n DTFT is, so double arrow indicates the DTFT relation. So delta of n minus 1 DTFT is, so whatever the DTFT is there, earlier DTFT, for that a phase factor will get added, which is e power minus j omega into n naught, where n naught is 1. So it is e power minus j omega is, so this is the DTFT of delta of n minus 1. So you can substitute by using again linearity property. You can substitute 1 here, and you can substitute e power minus j omega in the frequency domain when you take frequency domain. Okay, so and he has already given that v of g power j omega is the DTFT of v of n. So substitute here v of j omega. Here also you need to use the what we call time delay property, so that it will become e power v of omega into e power minus j omega. Here also delay is 1, so e power minus j omega into 1. So p naught into 1, p1 into e power minus j omega for this delta of n and delta of n minus 1. So from this v of g e power j omega, if you take common, so you'll get p naught into p1 e power minus j omega divided by d naught into d1 into e power minus j omega. So this is the dtft of v of j omega from this equation. So this is, remember this kind of things we use in system analysis. So in discrete in analyzing discrete time systems, we use we need to know what are the poles and zeros, or some like that. Okay. This actually is okay when you treat this as a system input output relation with v of n as output. So this is a system, v of n is your output and the delta of n is your input. So then this v of n is the impulse response of the system s. Okay, what is the input output relation between this one is this one. So the Fourier transform of impulse response is called frequency response of the system. So this will become frequency response of the system. So from here, by substituting omega different values minus pi to pi, you can see how the system is behaving. Okay. So when you plot the magnitude of here, I don't know whether he plotted or not. No, he didn't plot it. So you can take some p0 and p1 values. Okay, you can just use MATLAB or Python. Just to put some p0 p1 values, d0 d1 values, and vary omega from minus pi to pi. Some frequencies, some interval, discrete frequencies you can take, because on system you cannot have infinite frequencies. You just take discrete frequencies like you can just plot minus pi to pi by taking some pi by 6, pi by 2, pi by 6, something like that. Okay, so you take some frequencies and plot this v of omega, okay, versus omega, and see and join all these amplitudes and see how the spectrum is looking like. Okay, whether it is a low pass filter or a high pass filter, you get some knowledge, okay, based on what frequencies it is allowing, what frequencies it is not allowing. Okay, it depends on p0 and p1 values. You change p0 and p1, d1 and d0 and d1 values by taking different sets. Okay, you will some point of time you will understand how it is varying, how it is depending on p0 and p1. Okay, so I will now and then I will ask a few questions to you. Okay, take this as a question. Okay, I will put a star mark here and with a circle. So if you answer this, okay, just mail me your answer, or you can send me through Piazza also a message, private message through Piazza. So if you can implement this equation, okay, on MATLAB or Python, and change d0 d1 p0 p1 values, and uh, give attach some plots and give your opinion. So I may give uh, like at least some bonus marks, at least 2 or 3 marks in the lab. Okay, 2 to 3 marks based on your okay. So this question, this analysis, okay, the frequency domain analysis of this system, whoever do this and send me the message, okay, or like mail me what your observations by changing p0 and p1 values for different values of omega. And if you understand for one set of p0 p1 d0 d1 values, how the behavior is, okay, so you will get a bonus mark in the whenever lab is there. I will note your roll number, and in the coming days you will get bonus marks. Okay, so clear till now? So if you have any doubts, you can just post in the comment section, or you have the WhatsApp number, send me the message. Okay, now moving on to another one, the energy density spectrum. So for this I told we'll uh, uh, see the correlation between the two signals. Okay. So anyway, from the Parseval's relation, what we had is energy in time is equal to energy in frequency. This is what just we have proved. Okay, and this is energy in time and this is energy in frequency. Okay, you just treat this as some again I will take p of omega. You can just treat this as p of omega d omega. Okay, so you are taking the area under this curve. Okay, you have some omega axis and from minus pi to pi. So this is some minus pi and this is some pi. Just assume that it would be mostly symmetric. Just assume that I am just taking something like this. Okay, this is p of omega. That means y axis is p of omega, x axis is omega, and this is the curve. Okay, and what is this integration mean? This is the average value of this curve. That means area under this curve. Integration means you are calculating the area under this curve you are calculating. So and dividing with the width. Okay, width is 2 pi. So that will give you the some average value of this p of omega. Okay, so this so what does this mean actually? This meaning is, okay, so you have uh, if you take one, for example, omega is equal to pi by 2. Okay, when at pi by 2 value you will get some amplitude. So what it is called? So that is the contribution of that particular frequency in the entire signal. So this is entire signals magnitudes. So when you take only one particular frequency, pi by 2 or some omega naught, so at so it is having some p of pi by 2 value. So that means at frequency pi by 2, okay, so you have this much magnitude. Okay, that is the this frequency pi by 2 is contributing this much magnitude in the entire spectrum. Okay, so we call that as uh, uh, this per frequency what is the contribution. Okay, so likewise we have pi by 3, pi by 6, 0.1 pi, zero point 0.2 pi, 0.3, 0.007 pi, something whatever it is. Okay, so for every frequency you have some contribution. So when you can plot, so this plot is nothing but that. Okay, you can for at each and every frequency you can find the contribution. Okay, of that particular frequency. So this we call it as per frequency, per one frequency what is p of omega. Okay, or p of omega is this square of this magnitude. So per single frequency you are calculating the square. So uh, actually we call this as this is kind of a density plot. So we measure how this uh, values are, how densely they are packed. Okay, how means like at what with respect to frequency, what is the distribution of this p of omega or mod g of omega square. Okay, with respect to the frequency, the distribution we call it as the distribution of p of omega we call density, similar to your probability density function. So you have data x, and if you find what is the probability of at each and every point of x, if you find what is the probability of this point x, so you will get some. If it is the x is continuous, we will call it as probability density function. Likewise, at each and every value of omega, you have what is the contribution of this omega, how much power it is, not exactly power, how much g of g omega square it is giving. So that plot we call it as this is like density spectrum. Okay. And what it is giving is, it is giving energy, so that's why it is called energy density spectrum. Density means per frequency you are for every frequency you are finding the contribution of what, of energy you are finding. Okay. So, and in which domain you are finding, in the frequency domain, that's why it is spectrum. So energy density spectrum means the density or the distribution of energy per frequencies. Okay, the distribution of energy per each frequency. For example, what is the energy at pi by 2 means, you plot this g of omega square, and at pi by 2 whatever value is there, so that is the contribution, that is the energy present, okay, in the signal, the portion of energy present in the signal at frequency pi by 2. Okay. So that is energy density spectrum. So this mod g of omega square is called energy density spectrum, so, or energy spectral density. So it is just an English word. Okay, some will call density spectrum or some will call spectral density. Both are same. So the area under energy spectral density gives you the energy. That means for all frequencies, if you sum, area is nothing but summing the contribution at all frequencies. Okay. Likewise, in probability density function, the area under probability density function is 1. Okay. So likewise, the area under this energy spectral density is called energy. So that's what this is the area we are calculating. Area under this energy spectral density means square of the magnitude of the DTFT. Okay. So this is what you should just understand. The definition of energy spectral density is mod g of omega square for signal g. Okay, it is represented by sgg of omega. So this is actually a second order statistics. Okay, if you see the probability concept, if you apply random process concept, this is one of the second order statistics. So the area under this curve, okay, divided by 2 pi is the energy of the sequence. So now calculate the energy density spectrum of this signal or the low pass filter that we have seen a few classes back. Okay, this have a simple uh, something like this with omega c as the cutoff. Okay, so it has the magnitude 1. Okay, so from this we have seen already area. What is the area? This is a rectangular pulse. Okay, so since I am just giving you a first initial thought, okay, this is a low pass filter we have seen already. In the frequency domain, when you plot DTFT, it will look like this, and when you square it, it is 1 square 1 only. So area of this rectangle is what? Uh, the width is 2 omega c, and height is 1, or length into breadth, and divided by 2 pi should be there. So this will give you omega c by pi. So omega c by pi is the energy of this in the frequency domain. So this actually this is the density the DTFT of HLP of n. If you find DTFT of HLP of n, this one. So when you substitute this in the Parseval's theorem, Parseval's one of the equation. So energy in time is equal to energy in frequency. So, and in the place of HLP of omega, you can substitute 1 when omega is between minus omega c to plus omega c, you can substitute 1 here. And from here also, this is what the integration of minus omega c to omega c d omega is 2 omega c divided by 2 pi, that is omega c by. So this is how we calculate mathematically by finding dt of t. Okay. So this is the signal. Find dt of t of this signal. This will that will be same as this one. Okay, that we have already seen in the previous slides. So now according to Parseval's theorem, so in order to find the energy in time domain, it is difficult to find energy. So for such signals, it is very easy to find frequency, the energy in frequency domain. So that is also you can treat as one advantage of Fourier transform. Okay, so in time domain, sometimes we cannot find energy or some information we cannot find so easily. Mathematically they are very complicated, but when you go to frequency domain, it is very, by using few properties, if you have some idea, it is very easy. So now it is just very simply you can find the energy as omega by c. So what is energy spectral density of this signal? So please comment. So I think you are commenting. So what is the yeah, you can just comment. Energy spectral density of this signal HLP of sin omega c. Energy spectral density means only this part. Area under energy spectral density is energy, but if you ask only energy spectral density, only energy spectral density means only this one. So HLP of e power j omega is 1, mod HLP of e power j omega is also 1, mod HLP of e power j omega square is also 1 square, which is 1. So energy spectral density of this is 1. Okay, if someone asks you energy spectral density of this sin omega c n by n, so which is let us say we call it as sorry, s h of omega, which is mod h of omega square. So this is 1 for omega, mod omega less than omega c, and it is 0 otherwise. Okay, so this is energy spectral density. Yeah, someone has commented correct answers. Good. Okay, so DTFT computation using MATLAB. So this is this we'll see in the lab. But if you are interested, you can just put it. You can just give. Okay, so you can use frequency z as a function in MATLAB. Numerator means you need to give p naught, p1, p and so on, pm, and denominator is d naught, d1 and so on, dn. Okay, just put this denominator coefficients only as an array you need to send. Okay, and frequency also as an array you should send what frequency values you want, like minus pi to pi you can divide into some 100 or so values, and you can pass them as an array in this for this function, and you will get h, and you can plot h. Okay, so for this example, p naught p1 are this one and d naught d1s are this one, and when you use that function, so h you will get real part and imaginary part. So if you plot only real part, and imaginary part. We won't get much information from here also, but if you take the magnitude, then you can see it is acting as some kind of low pass filter. So from 0 to pi by zero point 0.6 pi, it is not allowing anything. After zero point 0.6 pi, it is allowing. So the cutoff may be somewhere here 0.7 by something like that. Okay. This is the phase, corresponding phase. So it is not linear phase. Okay, some here it is linear, but here it is not so linear, close to linear. Okay, as you said, phase has discontinuities in DTFT spectrum minus pi. This after 3.14. So here this is pi, this is minus pi. There will be discontinuity. Okay, actually this should come on the top here from like this smooth. So this is unwrapped phase. This is the unwrapped space phase. For that we use some this is like not, we don't have not now it is out of scope for this getting unwrapped phase from phase spectrum. There are several methods. So in advanced DSP you can have this. So now this is very important topic, not in DTFT but in the next coming classes. So how to find linear convolution using DTFT. So we use this convolution property. When you convolve these two signals in frequency domain, they will get multiplied. The spectra will get multiplied. Okay. So multiplication is easier in on DSP processors. Okay. So that's why what we do generally do is, when you want to find the convolution of two signals, first to find their DTFTs, multiply their DTFTs, and then take IDFT. This block is same as convolution. This block, okay, from here to here. So assume this is a convolution block. So it is performing a convolution. This is a convolution symbol, linear convolution. He has given, okay, circle. Okay, let us put circle. So you have one signal coming through and another signal coming through like this. So here you have x and here you have y. Okay, x of n and y of n. Or so for example, or h of n. This is h of n. The output is y of n. So generally what we do is y of n is a summation over k x of k. In time domain, if you calculate, this is h of n minus k. So this is what we do in time domain. Okay, summation over k x of k h of n minus k is y of n. This is linear convolution in time domain. Instead of computing this, okay, instead of implementing this, what we can do is, if you find DTFT of x of n, that is h x. Okay, so y of j omega is the DTFT of x into the DTFT of y. Okay, so that will give you, until this it will give you in the frequency domain. Okay, so this block will perform convolution and DTFT. So this multiplication is same as, until this is the convolution property. Okay, for if you want to get in time domain, you need to take IDTFT, inverse discrete time Fourier transform. You will get y of n. Okay, so there are 3 DFT blocks you require and 1 multiplier you require to find a linear convolution. Just remember this. Okay, to find a linear convolution, what is the hardware you require? 3 DFT, 3 DTFT blocks, Okay, that includes 2 DTFT plus 1 IDTFT. Okay, and one multiplier. Okay, later we'll show that if you convolve like this, okay, in using by using time domain, okay, you will take few computations like multiplications and additions. Okay, you need to multiply these two. Okay, delay anyway, it is just a memory. Delay we don't take much care. It is just like a memory. We'll store all h of n's at one place. And this is summation. That means we have additions. Okay, you have multiplications and additions. So the number of multiplications and additions required to find the linear convolution between two signals. Okay, directly in time domain. Let us say this n1 by using DTFT. If you implement like this, okay, instead of directly doing this, you use the properties of DTFT, find DTFTs first and then multiply and then find DTFT. Later we have some efficient algorithm to find the DTFT that we'll see later. With that efficient algorithm, let us say n2 or the number of computations. As the signal length increases, this n2 will be very less than n1. So the number of multiplications additions you do in finding linear convolution in frequency by through frequency domain properties, okay, properties of DTFT, or we'll say later that is called FFT, is far less than when you perform linear convolution directly in time domain. Okay, for that this is very useful property. Okay. So phase unwrapping is one thing we actually is basically out of scope. We don't discuss now. So and the definition of frequency response. Okay, as we said, uh, okay. So yeah, for this I will just would like to use this board. So you have a system like this, and x of n is the input. Let h of n is the impulse response of this time discrete time system, and y of n is the output, which is the convolution of x of n and h of n. So which is same as when you put this convolution equation, this is x of k, this is h of n minus k, where k is varying from minus infinity to infinity. So unless there are finite limits, I won't put any limits here. Okay, you just follow that. If no limits are there in my writings, that means that is minus infinity to infinity, or in frequency domain that is minus pi to pi. Okay, so this is the convolution. So what I will do is, if x of n is e power j omega n, some complex exponential, if I take, okay, then what happens, or this is same as what we can write, it is same as, yeah. Okay, so when you substitute in the place of x of n e power j omega n, what you will get, summation over k e power j omega k h of n minus k. Okay, so now this is now you can put n minus k as some p. Let n minus k is some p. this will be summation over p. The limits won't change from minus infinity to infinity. So in the place of k, you will have n minus p. So what we can do is, yeah, e power j into omega into, in the place of k, you will have n minus p, and h of p. Okay, when you divide this, okay, this into this exponential is divided into two factors. One is e power j omega n, and another is e power minus j omega p. Multiplication between these two is this. So e power j omega n is independent of p. It can come out, you can write outside this summation. So this is summation h of p e power minus j omega p. I'll write somewhat closer, e power minus j omega p. So this is over p. What is this one? This is like summation over n h of n e power minus j omega n. This is nothing but the dtft of h of n, or here in the place of n p is there. So this is nothing but h of omega, dtft of h of n, if you call it as h of n, so it is h of omega. So what is this completely now? What is y of n from here? So this is all y of n only. So this is y of n, this is y of n, so this is y of n. So we got finally y of n as h of omega into e power j omega n. So if you give input as e power j omega n, what will be the output of this? Is an LTI system. We only deal with LTI systems. What is the output of the LTI system? We get h of omega into e power j omega n. So such kind of signals, okay, when you give the as input, the output also you get same signal, but some, what we call, a constant. So this is independent of n. This is some constant with respect to n. Okay, some constant a into e power j omega n. So such kind of signals we call it as eigen functions of signal is a function, so it is a eigen functions of a system, LTI system. So all complex exponentials are eigen functions. Okay, that's what it is given here. So most discrete time signals, linear combination of sinusoids. Sinusoids is nothing but complex exponentials. Okay, so if you know the LTI system to a single sinusoid, then we can find more complicated signals by using linearity property. Okay, so the important property of LTI system is eigenfunctions. That means when you give eigenfunction to an LTI system, output is also same function but just multiplied by a complex constant. Here our complex constant is h of omega. Okay, so that's what the summary of this slide is, whatever we have done the math behind this side. Yeah, it is given here also. Okay, same thing here, it is given here. So in the place of here, he has taken the second like convolution is commutative, x of k into h of n minus k, or h of k into x of n minus k, both are same. So in the place of x of n, you take complex exponentials, you will get finally y of n is some complex constant. This is complex constant. H of e power j omega is the complex constant, some a. So complex constant into the same signal, x is e power j omega n. So y of n is some complex constant in the same signal. Such signals we call it as eigen functions of the system. Okay. So that is the definition of what is the use of these eigenfunctions as it is mentioned in the previous slide. So this is a sinusoid, complex sinusoid. Okay. So when you find the response, if you can find the response of one complex sinusoid, for other complex sinusoids also you can find, only it depends on the frequency of this sinusoid. Okay. So here omega is there, here omega is there. Okay, for example, what I mean is, okay, if you give e power j omega naught as input to a LTI system, the output will be h of omega naught into e power j omega naught n. So this complex constant h of omega depends on the frequency of the input j omega naught. So you will get h of omega naught. So if you give e power pi by 2 into pi by 2 n, e power j pi by 2 n as input to this system, what will be the output? H of pi by 2 into e power j pi by 2. Now in the place of omega, first one when omega is equal to omega naught, this is the equation, this is the output we get. When omega is equal to, in the place of omega naught, if I put pi by 2, this is the equation. Okay, for each and every frequency this value will change. Okay, for omega naught you will get some constant. For when omega is equal to pi by 2, you will get another constant. Omega is equal to pi by 6, you will get another constant, something like that. Okay, so this as the frequency as of the input changes, omega naught, pi by 2, pi by 3 and so on, the output scaling factor will change. Okay, the scaling factor of the output will change. So this this scale depends on the, this scaling factor is depending on the input frequency. So it will give, what it will give is this h of omega depends on what, h of n or h of k. So it is the characteristics of the system, because h of k is the impulse response of the system, h of omega is depending on the impulse response of the system. This h of omega will now giving the characteristics of the system in frequency domain. Okay, h of k is representing the characteristics of the system in time domain, where h of omega is giving the characteristics of LTI system in frequency domain. That's why it is called frequency response of the system. Frequency response of the LTI system, this h of omega is called the frequency response of the LTI system, because the response of the system depend on h of omega. Okay, or the in a particular frequency, for each and every frequency how the system is behaving. For example, you may get here, for example, assume it is a real, I'm just giving. So for omega naught, it may, omega naught is equal to pi by 6, let us say. So it will give 5 as the scaling factor. When omega is equal to pi by 2, it may give 2 as the scaling factor. It depends on the frequency. Okay, but it is just a complex number. It should be a complex number. I'm just giving you for understanding purpose. Okay, for different omega values you will get different h of omegas. So that will give, that characterizes the LTI system in the frequency domain. So we call it as frequency response of the LTI system. So that is the concept of eigenfunction and frequency response. What is the eigenfunction? When you give a signal input to an LTI system, the output should also be the same signal but multiplied with some complex constant. Okay, constant is with respect to n. Okay, here h of omega is not having any n term here. Okay, this is function of omega, it is not function of n. So it is considered as constant with respect to n. So when you give an input, okay, x of n, the output should be a into x of n. A is h of omega there. Okay, so what is that a? That a is h of omega, and it depends on the system's impulse response. So that's why we call it as frequency response of the system. In frequency domain, it is representing the system's impulse response. Okay, so impulse is a time domain name. So when you give delta of n to a system, whatever response we are getting, we call it as, okay, impulse response h of n. And if you take dtft of this one, so this dtft is h of j omega, that we call it as frequency response. So what is the relation between impulse response of the system and frequency response of the system? Frequency response of the system is just the dtft of the impulse response of the system. Okay, and by definition, what is the impulse response? When you give impulse signal, when you excite the LTI system with the impulse signal, that will give you the impulse response. What is the frequency response? Frequency response means at what frequency, when you vary the frequencies, how the system is behaving. Okay, when you take the input, when you vary the input frequencies, monotonic frequencies like omega naught, or varying from minus pi to pi, when you vary the frequency, how the system is responding to that particular frequency, it is given by the frequency response. Okay, so it will give the frequency domain description of the system, whereas impulse response will give you the time domain description of the system. So more clearly saying, if so we'll take next page. If someone plots you, uh, let us say, I will take the low pass filter only. This is omega c and this is pi. Forget about the negative frequencies as of now. So this is h of omega, it is 1. What does what does it means? Okay, so h of omega varying from 0 to pi, it is behaving like this. So this is representation of a low pass filter in frequency domain, and its impulse response is h of n. Okay, so when you give a complex exponential e power j omega naught n, what is the output? Output is h of omega into e power j omega naught n. So output y of n is equal to h of omega into e power j omega naught n. This is from the eigenfunction, because e power j omega naught n is the eigenfunction. So this is the eigenfunction. The output is this. Okay, this is the constant. So omega naught means here also you will have h of omega naught. Okay. So now if omega naught is less than omega c, if omega naught is less than omega c, what is h of omega naught value? It is 1. When omega naught is less than omega c means somewhere between 0 to omega c, whatever the value you take between 0 to omega c, some omega naught here. Okay, So its value, h of omega value is 1 here. So this is 1. So that means y of n is equal to, so I should have written started from here. So okay, so y of n is equal to 1 into 1 1 into e power j omega naught n when omega naught is less than omega c, because here h of omega is 1. If omega naught is greater than omega c, so somewhere here, now omega naught is somewhere here greater than omega c, h of omega is 0 here. Okay, this is 1, this is 0. So h of omega is 0. So here 0 into e power j omega naught n will come. So this is 0 into e power j omega naught n, which is 0 only. So y of n is 1. So it will give the same output as that of input, as long as the input frequency is less than omega c. This omega c, you can call it as cutoff frequency. As long as the input signal is having the frequency less than the cutoff frequency, it will give the same input as the output. If the omega is greater than omega naught is greater than omega c, that means if the input signal frequency uh, exceeds the cutoff frequency omega c, then the output will become 0. Okay, for example, you have two sinusoids like this. One is low frequency and another one is very high frequency sinusoid, something like this. This is x of n. Let us say until this point, until n1, you have this frequency which is less than omega c, and this frequency is greater than omega c, very high frequency signal. When you give this as input to this, what will be the output? The output will be up to n1, you don't have any you will have just a scaling factor. Okay, it will get multiplied with 1. So you y of n is same as x of n, and after n1, since this frequency is greater than omega c, okay, so it will be, output will be 0, because h of omega is 0 after omega c. So because this is as I said, this is actually acting as a low pass filter, so it will allow only low frequencies, and high frequencies it won't allow, it will discard. Okay, so this is the intuition of a frequency response of the system. So for what frequencies, what is the response of the system? For all the frequencies less than omega c, the response of the system is good, 1. For the frequencies greater than omega c, the response of the system is 0. That means it won't respond to the frequencies higher than omega c. So that is one particular for this system. So likewise, by knowing the frequency response of various systems, you can by plotting the frequency response of different systems. For example, you have this system like this. Okay, this is 0 and this is, now it is like from omega c to pi, it is 1. So that is h of omega. So that means this system, so this is also a system with h of n as impulse response, and h of omega is nothing but the dTft of h of n, and if you take x of n as input and y of n is the output. Okay, so as long as x of n frequency is in between omega c to pi, okay, sorry, so as long as omega c frequency is between 0 to pi, it will allow all those frequencies, and those frequencies which are less than omega c, it won't allow. Okay, these frequencies it will allow, it won't allow, means the the impulse response, the frequency response of the system is 0 for those frequencies. Okay, the frequency response of the system is 1 for these frequencies, omega c to pi. Okay, that is the by knowing the, by plotting the frequency response of the system, by knowing the frequency response of the system, for what frequencies, what gain it is giving. So this is nothing but gain. That is output is nothing but h of omega into x of n. Okay, that is for eigen functions. Okay, once you analyze for eigen functions, other functions you can always represent as eigen functions, that we see later. Okay, so this is what frequency response of the signal mean. Yeah. And since it is a complex quantity, it's a complex constant, we said, with respect to n. So it has the real part, imaginary part, magnitude, and phase. So the magnitude response of the magnitude, we call it as magnitude response of the system, and phase we call phase response of the LTA system. Okay. So overall h of omega is called frequency response of the system. Since frequency response of the system is a complex quantity, it has magnitude response and the phase response. And this magnitude response, if you for example, there are very minor variations in the magnitude in some cases. Okay, where the magnitude response will be something like this. So some minor variation, something like this. We don't understand what is happening in this gain if you plot simply h of omega versus omega. When you take a logarithm of this, okay, so 20 log or 10, whatever, this is just a constant. So we'll get 20 log of mod h of omega. This is base 10, where it enhances this uh, variations here. Okay, it will map to a nonlinear scale. Log is a nonlinear okay, sorry. So log is a nonlinear operation. Think, okay, it is gone. Okay, yeah. So this minor variations, when you apply log, they will be these minor variations will be enhanced. Okay, so this will map to a larger scale. Okay, so that's why we'll take log. Okay, and since the units for this, gain has no units. Okay, gain is input by output. So later we'll see h of omega is also the dtft of output by dtft of input. It has no units. So this also log also won't have any units, but we since we'll take with respect to log 10. Okay, we'll call it as decibel. Deci means 10, so log is with respect to 10. So it is we'll take it as decibels 20 log something, we'll take in dB. Okay, so when 1 h of omega is 1, or mod h of omega is 1, it corresponds to log 1 is 0, so it corresponds to 0 dB. So this we call it as unity gain. Unity gain in terms of plane terms, but unity gain corresponds to 0 dB. So unity gain, you don't think it as 1 dB. Okay, it is 0 dB. So that's why we'll take everything in log for enhancing this gain region. So and yeah, if you g of omega is this one gain function. The negative of the gain function, we call it as attenuation loss. Okay, if gain is low, you call it as loss. So this already we know for if x of n is real function from the symmetry properties, its magnitude spectrum is symmetry, even function of omega, and phase will be the odd symmetry, odd function of omega. So this is one example. Once you know h of n, if you find it dtft, that will be your frequency response. For example, moving average filter, if you take moving average filter means it will have all ones, okay, m number of ones, and the height of okay, m number of samples. It is nothing but a rectangular pulse, okay. So the moving average system is simply like this. So 0 to and so on, m minus 1. The length is m and the height is 1 by m. So the height is all will have same height, 1 by m. So this is h of n, okay. And when you pass any input to this system, what it will do, what will be the output? It will calculate the average of this m samples of every m samples of the input. So what you can take it, h of k x of n minus k is the convolution. This always happens. So this is nothing but summation over k minus infinity to infinity x of k h of h of k and x of n minus k. So this one, when k is equal to 0 to m minus 1, what happens when k equal to 0 to m minus 1? This h of n is 1 by m, otherwise it is 0. So you can put 1 by m here in the place of h of k, and this is x of n minus k, which is 1 by m times summation k is equal to 0 to m minus 1 x of n minus k. What is this y of n? This is called what it will do when you expand this, y of n is equal to, when k is equal to 0, what happens? So this 1 by m is a constant, it will be outside. When k is equal to 0, this is x of n, plus when k is equal to 1, this is x of n minus 1, and so on. And the last term will be x of n minus m plus 1. So likewise we have, this is k is equal to 0. So these are m samples, past m samples of the input, okay, m samples of the input. So these m samples of the input are added and divided with m will give you the average of these m samples at n, that is y of n. Output is the average of the so when n increases, again you will get new m samples and you will get another new value. So for a given input, okay, so I'm just plotting a continuous time signal. You treat it as samples. So you take a window, So you take a window of m and you keep on moving this window over the input. So for every shift in this window, you will get a new y of n. Okay, n is varying from, this is maybe for 0, this is 1, 2, 3, and so on, y of 0, y of 1, and so on. So that means this is a this window, you are moving this window over the input signal, okay, and calculating the output. That is the moving average system. What is this window is doing? This window will average the input samples and it will give as output. So that is the moving average system. What is the impulse response? This impulse response is nothing but a simple uh, a rectangular pulse. Okay, if you take it, this is nothing but a rectangular pulse of width m, and height 1 by m. For such signal, this is the impulse response 1 by m for 0 to m minus 1, 0 otherwise. So for this you can calculate DTFT very easily. So this DTFT is this one. When you plot this DTFT, it will be a sinc function. So and so if you want to see more, uh, so this is the DTFT for different m values. M14 means 14 samples it will take and average. M5 means only 5 samples it will take and average. This is the order of the moving average filter, or we'll call m point moving average system. So when m is equal to 14, this blue line, that means it will act as a, what filter it will act as? This is frequency and this is the magnitude. So it will act as a low pass filter only, but the cutoff frequency is very less here, around zero point 0.1 only the cutoff frequency is there. So when you take m is equal to 5, now this is the red line is the magnitude response, and here the cutoff frequency is greater than the previous one. Okay, so when you increase the order of the moving average system, it will become more and more low pass. That means the cutoff frequency decreases as m increases. Okay, and it has linear phase. You can see here, this blue lines or red lines are following lines. This discontinuity is due to phase wrapping effect that we have in DTFT. Okay, so yeah, this we'll see it. So this is one example for what we call frequency response of the system. This is the magnitude response, and this is the phase response of the system. We generally don't consider the phase response as of now. We just see it is linear or not. So later we'll see what is the importance of phase. As of now, just see the magnitude. As m increases, the cutoff frequency is decreasing. Moving average is nothing but a low pass filter only. So it is a low pass filter. Okay, so can you just assume that okay, that I will give it as a uh, attendance question. So if you have any doubts as of now, just share in the chat box. We'll see. uh, so are there anyone who yesterday, two or three people didn't mark the attendance they said? Okay, just uh, give your for me, only two people are asked, two or three. So those three, just type your ID numbers in the chat box so that I will update. All others I won't. Okay, only those two three I will give. So meanwhile, if you have any doubts, you just post in the chat box all regarding all the concepts we have seen till now, right from the properties, Parseval's theorems to the frequency response of the system. Also give your section yesterday, whoever have. Hope we can see this thing in the chat box. Yeah. So the board, for few, the screen is not clear. You should actually uh, change the YouTube the settings at least to 360 pixels. Okay, you might have getting, you might be keeping only 144 pixels as your setting. So just change your settings. Okay, so you'll have only 3 minutes to submit the attendance. So please, okay, 1 to 1.5 minute, you can just think what is the moving average system, what it is giving. As the thing is, as m increases, the cutoff frequency decreases. What it will give as m goes to infinity.